Okay, everyone. Now we're going through sections 8.1 and 8.2, which is systems, beginning systems of differential equations. So first, a quick recap. When we were dealing with just individual differential equations, we started off, we never looked at one this messy, but this is a type of thing which is an actual DE. It's a second order DE. Look how messy it is. It's certainly not linear because you're taking the sine of the second derivative and you're taking the ln of the function itself. And so anyway, that's an example of a DE. We didn't even try something like that. We restricted ourselves, well, to either ones that were separable or ones that were linear. Here's an example of a linear second order. Remember, to be linear, what do you have to do? The function and its derivatives, you don't do anything to that. You can do whatever you want with the variable, but the function and its derivatives, you just leave those alone. So that's a linear second order DE. We didn't try to solve anything that fancy either. For the second order ones, we restricted ourselves to basically things with constant coefficients there. Okay, and we're gonna do something similar coming up here. But anyway, now we're going to go to systems of differential equations. So instead of having just one function that you're concerned about, you might have two. So these might be the populations of two different animals that are somehow interdependent, like foxes and rabbits, right? Where the population of foxes affects the rabbits and the population of rabbits affects the foxes. All sorts of examples exist in nature where you have a couple of things that interact. We're going to see a bunch of them here upcoming. So one example then of a linear system is something like this, where this is a first order linear system, where or not linear system, but a first order system, where the derivative of x is given by this and the derivative of y is given by that. Notice that it's not linear because, again, you're doing various things. You're multiplying the functions together. You're taking e to the y, all sorts of things like that. But anyway, that's an example of a system of differential equations. You can also write it like this, and we will write it like this, kind of in vector or matrix form. Here's x prime, here's y prime. X prime, the derivative of x is equal to this. The derivative of y is equal to this, and these two things together make up the vector x. For lack of better notation, we use x both as one of the functions, but we also use a capital one with or it could be a small one, but with a vector over the top. Excuse me, to denote the whole system. So if you go through what I go through in the book and go through the process of looking at the definition of the derivative, you will see that the derivative ends up giving you, similar to a scalar valued function, the limit of this thing at one point in time minus at another point in time divided by h as h goes to 0. So in particular, the graph of the solution of this system could be any old thing. It could be something like this that goes around, and so basically at various points of time, depending on what these derivatives are telling you that's happened, this thing is going to be moving around and can intersect itself and do all sorts of crazy things. And the thing to note is that if this is x of t right here, and this is x of t plus h right there, notice that the difference in those two vectors is this pink one. I don't know if you can see it. Let me put it in black as well. It's that one right there that goes from here to here. So there's the difference, and you divide that by a scalar, it's still going to be the same direction. And so the moral of the story is that the derivative is always going to give you basically a tangent to the graph. So it's going to give you a tangent to the graph at any point. It's basically going to give you the direction in which the thing is going, and then the speed with which it's going, that's basically the size of it. But the direction is going to give you the direction of the graph. So anyway, I want to mention that, and then in particular, we're not going to do anything close to that complicated. Here's one thing we can do to make things less complicated right off the bat. We restrict ourselves to autonomous systems. Autonomous means that you never see any t in here. It just depends on the values of x and y. And when we make these restrictions, there's still going to be all sorts of physical phenomena that can be described in systems. So we're leaving off a lot, but we still have a lot that we can play with. A lot of different natural phenomena that we can model this way. So this is an autonomous system. Notice there's no t in there. And so if you were to graph that, one thing difference between this graph and this graph is that this graph can intersect itself. Because at one point in time, you're right here going this way, and then at another point in time, you're right here going this way. So that's fine that at different points in time, you happen to be at the same point. Here, if this is the graph of this, there's no way that this graph could cross itself, because basically what you're saying is that if you're right here, it doesn't matter what the time is, given right here, this system has to be able to tell you which way you're going. And you've got a couple different options for which way you go there. So my banana breads are done. And so anyway, this is when you have an autonomous system, then it can never intersect itself like that. Okay, so that is section 8.1. And now, since I tell you what, maybe it's easiest since my banana bread is done, just to let that be 8.1. We'll just leave it at that, and we'll start another one for 8.2. So 8.2 basically says what are different places where we actually use systems of differential equations. We'll get into that next time. Okay.